Welcome to the Wastewater Treatment Certification Training webinar series. This is Chapter 3, Biology, and the presenter is John Walker. Activated sludge is a biological process in that activated sludge is a mixture of bacteria and other microorganisms which digest anything that is biodegradable, and we can call that food, that is present in wastewater. The biological process is dependent on the bacteria and protozoa that are present both in the activated sludge and bacteria that come in wastewater. And if we can control the growth of these microorganisms, then we can determine how efficient the treatment is going to be. And the growth of microorganisms, bacteria and protozoa, is influenced by many factors, not least the amount of food that comes in, the organic material that comes in the waste, the pH and temperature, and the dissolved oxygen in the treatment process, plus a few others that we will discuss later. So this activated sludge is a mixture of bacteria, protozoa, these can be amoeba, ciliates, and flagellates, and something that we call metazoa, which are small multicellular animals. These are rotifers, nematodes, and what we call tardigrades or water bears. And the microscopic examination of the protozoa and metazoa also can give a good idea of how well the treatment of activated sludge and wastewater is happening. Just as an idea of how much biomass is actually bacterial, it's about 95% of the activated sludge is actually living organisms. So these bacteria, protozoa, they grow in the wastewater by eating or consuming anything that is biodegradable, proteins, carbohydrates, fats, and other compounds, very much like you and I with our diet need a good all-round combination of all of these things. The next few slides are going to talk about definitions that are useful in understanding how this process will work. And this slide shows two, something that we call synthesis. And synthesis is the process by which cells can be made and cell materials are produced that are important in making a new cell following the absorption of materials and compounds from the wastewater. In order for synthesis to occur, you have to have energy, and the term respiration is what we call the process of making energy from carbon, organic material. We also call this BOD5. We can also call it food, very much, again, like you and I have to eat in order to get energy. So in a way, this is a cycle. To get good synthesis, make new cells, you need energy, and respiration needs a living cell in order to occur. So you can't have one without the other. This is a slide that shows you what we refer to as cellular respiration. Here you can see a glucose molecule, and in the presence of oxygen, The cells break down glucose, give off carbon dioxide, water, and something called ATP, which is the energy currency of the cell. And the cell uses ATP to do all the synthesis and make more energy in the cell. So you can see here that if we take glucose, put it in a beaker and set fire to it, 100% of the energy contained in the glucose is given off as heat and light. Whereas if the glucose that we consume, about 40% of it gets converted into ATP, and we're a little more efficient than a car that will burn gasoline to move, which is only about 25% efficient. So we're not doing too bad. Wastewater contains a lot of things, and the parts of this that we're most interested in is in the carbon material that the bacteria can use for energy. So this flow diagram shows that if we look at the total organic carbon present in wastewater, some of this is not usable. We call this non-oxidizable because the other part of this that can be chemically broken down into CO2 is chemically oxidizable or chemical oxygen demand. And within this group of organic material, there is some that bacteria and protozoa can't use. We call this non-biodegradable. And of course, the other part that bacteria will use, we can call degradable or biodegradable. And this is the BOD, or biochemical oxygen demand. Within this group, there are complex organic material. These are large molecules, large proteins, polysaccharides, things like this, that take a while for the enzymes or the bacteria to digest. And these get broken down into simpler molecules, these that the bacteria can take up directly, can absorb directly into the cell and use them very efficiently. So here is a description of each of those that I introduced on the previous slide. Here we have total organic carbon. This is a measure of the carbon dioxide that's given off when you heat anything to 550 degrees centigrade. This is what happens when you burn wood. You're looking at the total organic carbon. Underneath that is chemically oxidizable carbon, or COD, and this is where we add a strong oxidizing agent like potassium permanganate and acid, and that helps to break down organic material in a chemical way. And then a smaller portion of that is what we call biochemical oxygen demand, or BOD, and this is where bacteria in the presence of oxygen are used to estimate how much carbon is in there that the bacteria can find useful. In the slide where I showed the flow diagram, I talked about complex BOD, and this is the chemical composition of wastewater where in order to the bacteria to use them, this complex organic material has to be broken down by enzymes that the bacteria produces and secretes into the wastewater. If you can imagine long chains of Lego blocks which are broken down into smaller pieces and individual blocks that the bacteria can then use. Simple BOD is simply that. These are small molecules, things like glucose, acetic acid, that the bacteria can absorb very easily. They don't have to be broken down outside the cell. They are used within the bacteria, and the process of taking them into the cell is absorption. So this is what a bacterial cell, a very basic bacterial cell, looks like. It's one cell, unlike us, that are made up of many, many, many cells. Inside the cell is simply what we can think of as a bag of soup. You have a cell membrane, like we do, around all our cells. You have a cell wall that protects it from lots of things that could damage the cell membrane very easily. Some bacteria have what we call a flagella that help it move. If you can imagine a tiny propeller swirling around to move the bacteria if it needs to. And inside the cell, there's not much going on. The DNA, the nucleic acid material, is shown here in red, and lots of other little things that we really won't need to talk about are also present. So just think of this as a bag of soup with a cell wall around it, and you get the idea of what a bacteria is. So a little bit more basic information about bacteria. They're small, they are a single cell. Some do have flagella and can move, and sometimes even those that can move will lose the flagella and become immobile. One of the great things about bacteria is they can adapt very, very quickly to changes in their environment, in amount of dissolved oxygen, the pH, presence of certain foods, temperature, other materials that might be in there, like total suspended solids. And so they can react and go to work breaking down the wastewater very, very quickly. They divide by splitting in two, very much like our cells do, but where our cells sort of stick around and make organs, bacteria just split in two, and 2 becomes 4, 4 becomes 8, and so on and so forth. We call this binary fission. Okay, splitting is fission, binary is in 2. And due to this process of reproduction, we can actually graph, we can see here on this graph, the growth of bacteria. The number of cells are here on this axis, and the time is on this axis here. And so we see this growth curve, and we'll come back to this and discuss this in a little more detail in a few slides. Some other bacterial basics is that bacteria excrete enzymes into their environment that help break down organic material so they can be absorbed into the cell easily. This excretion of enzymes is part of what we can call slime. Slime is actually it's polysaccharides and proteins and fats. We also call this the extracellular matrix, but I think most people know this as slime. And this slime helps to trap food, carbon material, and it also helps to keep bacteria close to each other so that they can talk to each other. And bacteria do talk to each other, but not in the way that we do, so they can respond to the environment even quicker. The good thing about slime is that ultimately this builds up enough to stick bacteria and organic material together and to form floc. And the important part of this is that floc allows the settling of the waste so that it can be removed as sludge. In the previous slide, I mentioned enzymes. And enzymes are the workhorse of the cell. They are proteins, which is one of the reasons why you need to eat protein in your diet. Bacteria are the same way. They are catalysts. That means they don't get used up. They keep on doing the same job over and over and over again. Everything that goes on in a cell, all the biochemical reactions, synthesis, respiration, etc., require an enzyme for the reaction to occur. And one enzyme does one job and one job only. So breaking down nutrients, making new parts of the cell, making energy through respiration, all depend on a specific enzyme to do a specific job. Enzymes are very, very finicky. If the temperature isn't right, the pH isn't right, other sort of factors in the cell aren't quite optimal, enzymes won't work properly. However, if the conditions are right, bacteria will thrive and do a very good job of breaking down the waste in wastewater. I talked about slime a little earlier on, and here I'm coming back to it. So one of the things that we can call slime, if we want to be use lots of big words, are extracellular matrix. We can also call it biofilm. So if you ever see those terms, they're really much the same thing. So slime, a biofilm, is a mixture of fats, carbohydrates, and proteins. This is food. We can also call it lipopolysaccharides. That's a really fancy word for saying fat with a lot of sugar. One of the great things about slime, when it's doing its job for us, is that it protects bacteria and binds food so it can be treated and used optimally. However, too much of a good thing is not a good thing, so excess slime can lead to problems in the treatment process if that is not taken care of. I mentioned also earlier that slime and bacteria are important in the formation of floc. So as the bacteria start to use the food, they grow, i.e. they increase in number. They develop either into small chains or clumps, depending on the bacteria. But the bacteria is still motile and actively seeking out the food, so they don't settle very well in these small chains or clumps. But you can break these up quite easily if you overmix. And so this is where the treatment process, not mixing too much, but mixing enough, is important in the formation of floc. Early on, when there's a lot of food, they haven't yet developed this slime layer, which can help them clump together in larger groups and initiate the formation of floc. However, as the sludge is allowed to age, the bacteria don't move as much. They will accumulate more slime. As this slime accumulates, then these clumps and chains stick together more, and then at a certain point, they will form what we know as floc. So if the organisms are grown under the correct condition, the floc can get larger, more compact, and begin to settle. I showed you this growth curve on a previous slide, and we'll come back and talk a little bit more about it. The first phase is the lag phase, shown here, where the numbers of bacteria don't seem to be increasing very much. So this is where the bacteria are getting used to their new environment, making enzymes and secreting enzymes based on what is in the water. They're building up all the materials they need to divide. And so you don't see an increase in number over a period of time. But then once everything's settled out, they get into what we call log phase. And this is where there is rapid increase in numbers. You can see here going from 100,000 to over 1 billion in the space of sort of a few hours. So at this point, the bacteria is growing as fast as they can because there is more food than bacteria, and food is plentiful. Here in this area, the cells are probably individual and maybe sticking together in small clumps, but not enough to make flock. After log phase comes the phase that we can call the stationary phase. And you can see here that the numbers of bacteria are not increasing, maybe even slightly decreasing. This is where the bacteria are not moving anymore. They've lost their flagella, they've switched it off. They've really started to secrete the extracellular matrix or slime and allow them to stick together, and a nice word for you, agglomerate into flock. Agglomerate is just another word for sticking together. If the flock get big enough, flock would settle to the bottom if we didn't do any more mixing or aeration. After stationary phase, the numbers of cells start to drop, and we can call this the declining growth phase. That's is because the food is running out. There is a little bit of cellular growth, but there's also a lot of dying cells. Here is where you have a lot of bacteria and very little food. And finally, the death phase. This is where the number of living bacteria keep on dropping, and they are just eating each other or eating themselves just to stay alive. And of course, if you were to not add any more wastewater at this point, the bacteria would just go into a sort of a hibernation phase where they wouldn't be growing very much at all. And of course, that's not going to do wastewater treatment any good. So of course, if you can imagine, you start to replenish the wastewater and you'll be back into this log phase again. The next set of slides are going to be a little bit of math for you. So we'll introduce this as gently as we can. But one of the parameters that is important in treating wastewater is something called the food to microorganism ratio, or F to M ratio. And by food, we mean the amount of organic material coming in that can be used by the bacteria for food. This is the biodegradable organic material, and we call this BOD or BOD5, and this is the biochemical oxygen demand. So food is organic material that the bacteria can use. And of course, microorganisms are essentially the bacteria and protozoa that will use this food to increase in number. And of course, reducing this food means that you are cleaning up and treating the wastewater. So microorganisms are the estimate of how many organisms are in the activated sludge process. We actually call this mixed liquor, and the volatile suspended solids. This is the organic material. And I mentioned earlier that 95% of the biomass is bacteria. So by measuring this MLVSS, which we'll talk about in another chapter, we're making an assumption that this is pretty much all bacteria. So the relationship of food to microorganisms is an important number to keep in mind. We can call this an operating parameter to figure out how well the sludge process is happening. So we can put some math into here, and the F to M ratio is the pounds of BOD5 coming into the plant on a daily basis, divided by the pounds of MLVSS that are present in our aeration basin or our treatment system. And this ratio is one that we can't give you an exact number, but over time you will figure out in your plant the F to M ratio that works best for your plant is the one that you will try and optimize. So this F to M ratio tells us about growth and the conditions of the cells. If the F to M ratio is high, there is a lot of food available, and the growth of bacteria are going to be as rapid as they can. If the F to M ratio is low, there is little food available, so the growth of microorganisms, the bacteria and protozoa, is going to be slowed down. The number here, you can see it varies widely, but a typical food to microorganism range in activated sludge can be 0.05 to 0.15. So the range for you is the range that produces the least amount of sludge whilst effectively removing the organic matter, the BOD. And in a plant, you need to reduce it by 85%. And we'll talk about that in a later chapter. Now, we can do some math on this. And so here is an example of a question that you would see in the manual or the math study guide. You may see in a test. So the question goes something like this. The flow to a 1 million gallon per day extended aeration plant is 0.8 million gallons per day. The influent BOD concentration is 161 milligrams per liter, and the concentration of MLVSS in the basin has been calculated at 2,450 milligrams per liter. What is the F to M ratio for this facility? So this is 2 pounds formulas, and let's look at how we would solve this. So that there is our formula, pounds of BOD coming in, pounds of MLVSS in the basin. So we calculate pounds of BOD, and here is the flow, 0.8 times 8.34 times 161 milligrams per liter. And if we do that calculation, it comes out to a little over 1,000 pounds of BOD coming into this plant average daily. The next thing we need to calculate is pounds of MLVSS. And again, here is the size of our basin. 8.34 is the weight of a gallon of water. And here is our concentration of MLVSS. And if we do that math, we get something 20,000 and a half almost pounds of MLVSS. So next slide will show you how we put those two numbers together. There's our formula. There's our pounds of BOD coming in. There's our pounds of MLVSS in the basin, and we divide one by the other. We get to an F to M ratio of 0.053. So here is one for you to figure out. And there is an extra little step in here for you because what we have given you is the MLSS of the oxidation ditch, but only 65% of this is volatile. So one of the first things you have to do is you have to calculate the MLVSS from the MLSS. So this is simply 65% of 3,400 milligrams per liter. The way that I'm going to do this math is I'm going to give you any time you want to solve this problem. And so I'm going to recommend that you pause the recording and then restart it when you've finished calculating this problem. This way you're not rushed. You can take your time. I'm going to, in a few seconds, show the answer and then go on to the next slide to show how we got that number. So if you want to now pause the recording, and when you have completed this calculation, you can restart and we'll go with the answer. So the answer is 0.06 as an F to M ratio. And then the next slide will show you how we do this. So the pounds of BOD in the influent are 3.2 million gallons per day times 8.34 times 188 milligrams per liter, which gives us a little more than 5,000 pounds of BOD coming into the oxidation ditch. The pounds of MLVSS in the oxidation ditch are 4.5 million gallons, which is the volume of the oxidation ditch, times our constant 8.34. And here is where we have converted the MLSS into MLVSS by multiplying this by 0.65, which is the decimal of 65%. And if you put all those numbers in the calculator, you end up with almost 83,000 pounds of MLVSS. So if now in the next slide, we divide the 5,000 by the almost 83,000, we get an F to M ratio of 0.06. I mentioned earlier that bacteria are very useful and need certain things to allow them to grow. And in order to sort of have some calculation of how much we are going to have coming into a plant, we use a term called population equivalence. And these are design values, if you like, so we can calculate how much water fluid is coming in and how much organic material is coming in from domestic wastewater. if the actual operating information isn't available. So they're an estimate of how much every person that is connected to your sewer system may add to what's coming into the plant every day. And this is a very simple analysis of those population equivalents. It's a little more complex than this, but this will do to give you an idea of how you can identify what is likely to come into your plant. So we're going to make an assumption that every person every day is going to flush down the sink or the toilet or the laundry, et cetera, about 100 gallons per day of water per person. Out of that, about 0.2 pounds per day is total suspended solids. So you can see that wastewater is over 99% water, has very little solid material in it, despite what you might think. And out of that 0.2 pounds of total suspended solids, about 0.17 of that is organic material that bacteria can use, the so-called BOD5. Out of this solid material and organic material, about 0.02 pounds per day is nitrogen, and 0.0048 pounds per day is phosphorus. We can also look at some more math, and this again is a design parameter. We call this hydraulic loading rate, and it's also known as the surface loading rate. And it is a number that is designed to give you the optimal flow into an aeration basin or an oxidation ditch, so that you're not going to overload the system. So the hydraulic loading rate, the formula for this, you can see it is gallons per day per square foot of surface area of either the basin or the ditch or any other system that you use. So here is an example that we will run through. What is the hydraulic loading rate or surface loading rate on a primary clarifier that's 75 feet in diameter, 10 foot deep, and has an influent flow of 1.5 million gallons per day? So on your formula sheet, you will see that we do have the formulas to calculate area when we have we're given diameter. Because we're looking at square feet, we do not need to be concerned with the depth of that clarifier. So here are the two numbers that we need: 75 feet diameter clarifier and a flow of 1.5 million gallons per day. Our formula for area is 0.785 times diameter. So since we've given you that in feet, there's no other conversion to be made. And those are the numbers that you should plug into your calculator, which should give you something almost 4,500 square feet. So the hydraulic loading rate, we've had to convert our million gallons per day into gallons per day. So that's in this number here, and it's divided by the area of the primary clarifier. And if we plug those numbers in, the hydraulic rate, loading rate is 339.7 gallons per day for every square foot of the primary clarifier. So if this is the design, then you have an idea of what your daily flow is to be optimal for the operation of that clarifier. Here is one that you can do. What is the hydraulic loading rate on the primary clarifier that is 20 foot wide, 60 foot long? We've given you the depth, which you are going to ignore, with a flow of 0.95 million gallons per day. And again, as in the previous math where you were given the choices, you can pause the recording, and when you've got the result of this problem, you can restart, and then we'll go through it on the next slide of how we got to the answer for this problem. So I'm going to give you a few seconds before I show the answer. So if you want to pause, please do so and restart when you are ready. So the answer is 791.7 gallons per day per square foot of clarifier. And let's look at how we solved that problem. So here are the numbers we were given. Here is our formula. So we need to know flow in gallons per day, and we need to calculate surface area in square feet. Our area is 1,200 square feet. And so if we do put those numbers in to this formula here we have converted 0.95 million gallons per day in 950,000 gallons per day, divided it by our area of our clarifier, and our loading rate is 791.66, and the answer we had is 791.7 because we've rounded this 0.66 to 0.7. And as a good tip for coming to any answer, all the four answers will be sufficiently different from each other that if you ever get close to 971, that's going to be the answer that you're going to need for this problem at least. We all do calculations slightly different, but the answers are never going to be 971.66, 971.7, 791.5. They're going to be sufficiently different that if you get close, because you're not getting exactly what we have because you're doing rounding errors or any other manipulation, you'll have the right answer. We're talking about organic loading rate, and this is similar to the hydraulic loading rate, but this is the amount of organic material coming in, and it is based on volume, not surface area. So hydraulic loading is area, organic loading is volume. And because the numbers can get very big, we actually have this in, rather than cubic feet, we have it in 1,000 cubic feet. So again, I will talk on this and how to solve this problem on the next few slides. So here we have a math question where the influent flow to a 2.5 million gallon per day extended aeration plant is 1.8, and the influent BOD is 198 milligrams per liter. What is the organic loading on this facility in pounds of BOD for every 1,000 cubic feet? So here's our formula. So you have to do a pounds formula, and then you have to figure out the volume of the aeration basin. And this is how we do that. So the pounds of BOD are the influent flow of 1.8 million gallons per day times our 8.34 pounds per gallon times 198. And that gives us something a little shy of 3,000 pounds of BOD. So what about the volume of the aeration basin in 1,000 cubic feet units? So let's look at this. So first of all, we convert million gallons per day to gallons. So this is 2,500,000 gallons, but we have to convert gallons into cubic feet. So we divide that by 7.48. These conversions are on your formula sheet. Please become very familiar with them. And that ends up being something like 334,000 and a bit cubic feet. So if you were to divide the pounds of BOD by this large number, you would get a very small number. So this is why we convert this number into 1,000 cubic feet units. So instead of 334,224, we now have 334.22 thousand cubic feet units. And if we go to the next slide, we will see how we put those two numbers in to get our organic loading. So here's our 2,900 pounds of BOD divided by 334.22 thousand cubic feet units, which gives us 8.9 pounds of BOD per 1,000 cubic feet. If we didn't do this, we would have 0.0089 pounds, which is not a very easy number to understand, and you can always miss a decimal point and be way off. 8.9 is a much more manageable number for us. This is why we do this conversion here. So here is one for you to do. And again, pause, take your time to solve this problem, and then I will show you the answer and show you the workings out. So the answer is 6.85 pounds of BOD per 1,000 cubic feet. And let's see how we solved this problem. So we need to know our pounds of influent, which is 1,832.3 pounds of BOD coming in to this plant. Our aeration tank volume is 2 million gallons per day, divided by 7.48 to get cubic feet, and then divided by 1,000 to get 1,000 cubic feet, which gives us 267.38. And so we're going to divide this number by this number. We'll see that here. And the answer is 6.85 pounds of BOD for every 1,000 cubic feet. I mentioned earlier that we have population equivalents to help us design a plant, and knowing how much waste is going to come in, then how much of that is going to be organic material, how much of this is going to be nitrogen and phosphorus. And this is important because bacteria, very much like us, need a balanced diet. And if they don't have the right ratio of components in their diet, they're not going to grow well enough to treat the waste. And at the end of this chapter, we'll go over what happens when you're taking in waste from very specific industries, and we'll see what you need to do to make the bacteria grow optimally. So we have what's known as the carbon, nitrogen, phosphorus ratio, and it is approximately 100 to 5 to 1. So for every 100 units of carbon, we need about 5 units of nitrogen and 1 unit of phosphorus. So if we analyze the C and P ratios and they're not in this sort of ballpark, then you're probably going to have some other nutrients to make the bacteria grow well. So in addition to carbon, nitrogen, and phosphorus, we need trace amounts of the other things, sodium and potassium, calcium and magnesium, iron and sulfur, and trace amounts of other elements as required. For the most part, in municipal sewage, the ones that we flush down from our homes, these nutrients are provided in adequate numbers, and we really don't need to worry about them too much. However, industrial wastes may have deficiencies, and again, we'll talk about this in the last few slides of this presentation. If that CNP ratio is affected, bacteria respond, and they respond by making more slime. I mentioned earlier that too much can be of a good thing, can be a bad thing, and one of the consequences of bacteria making more slime is what we call slime bulking, and that means that the flock doesn't settle well. So again, this is another reason to have the optimal ratio of carbon to nitrogen and phosphorus. Those people who are gardeners will know that you have to fertilize plants with nitrogen, phosphorus, and potassium in order for the plants to grow well. The same is true for bacteria in a wastewater plant. If you have nutrient deficiency at all, of course, the cells don't, the bacteria don't grow as well, and their ability to remove BOD from the wastewater is reduced. I mentioned that bacteria make extra slime, and of course, more slime on the outside of the bacteria will reduce the absorption of the nutrients that the bacteria need. The slime layers form sludge bulking, and so the flock won't settle. And because of nutrient deficiencies, there might be a greater growth of what we call filamentous bacteria. These are bacteria that form long chains, and again, this leads to poor settling of flock. And if this happens, you have to distinguish between whether this bulking is due to slime or the growth of filamentous bacteria, because you will deal with those in very different ways. We're going to talk now a little about the other requirements that bacteria have in order for them to grow well and to do a very effective and efficient job of breaking down waste. If you remember going back to an earlier slide where I showed you respiration and I showed you glucose and oxygen, most bacteria in an activated sludge require oxygen to grow, and if you don't have enough oxygen in there, it doesn't go well. So oxygen is used pretty rapidly if the bacteria are growing at their maximum log phase. The great thing about this process is we've made use of it in the BOD test, and the BOD test determines how much oxygen is used, and we make then an assumption of the amount of oxygen used tells us how much organic material is present in the sample. So in order to understand how oxygen moves through water and gets into water, we have to understand the process of diffusion. So oxygen is constantly entering and leaving the water through the water surface. This also depends on the temperature. The higher the temperature, the more oxygen moves in and out, and warmer temperatures have lower oxygen concentrations. This is due to the process shown here in these beakers of diffusion. So if I have a beaker full of water and I drop dye into this part, if I just leave it over time, that color concentrated here will slowly diffuse to show at equilibrium just a constant equal color throughout the beaker of water. So diffusion is the movement of anything in air or a liquid from an area of high concentration to an area of lower concentration. As I mentioned in the previous slide, the levels of dissolved oxygen in water is dependent on temperature. When water has the highest concentration of dissolved oxygen it can hold, we say that that water is saturated. And so water will only contain as much oxygen as it can at that temperature. Oxygen is important because most bacteria in an activated sludge system require oxygen in order to grow and make energy. Although there are some types of bacteria that can grow with less oxygen, and there is a group of bacteria that we call anaerobic bacteria, where oxygen is actually toxic to this group. And one of the ways you will know that anaerobic bacteria are present in the system is that in the absence of oxygen, they use lots of other stuff. And one of the products of trying to grow in the lack of oxygen is hydrogen sulfide, which is that rotten egg smell that you might come in contact with. Because oxygen is so important, we try and maintain the DO concentration in activated sludge at about 2 milligrams per liter. That seems to be optimal so that bacteria, even in flock, get enough oxygen to grow. If the DO is less than that, there's less oxygen to diffuse across the flock. The bacteria on the inside start to die, and this can cause the flock to break up, and therefore it won't settle. In order to metabolize food and produce new cells, an estimate of the amount of DO is about 0.1 to 0.3 milligrams per liter, which is where the 2 milligrams per liter is so much in excess, these bacteria will hopefully never be starved of oxygen. So there are lots of ways in which we classify bacteria because they're small and a single cell. They're not like we can look at different animals and plants and and identify them and classify them easily. We like to put things into groups, and so we can put them in based on their shape, based on their specific biochemistry, what substances they will use and what they make. Of course, their oxygen needs, which I'll show on this slide, and the range of temperatures that they grow at. So one of the very simple ways for us in the water industry is to divide them into aerobic bacteria. These are the bacteria that need free oxygen in order to survive and grow. I mentioned in the previous slides that anaerobic bacteria, if free oxygen is present, it is toxic to them and they won't grow. But there is another group we call facultative, and these bacteria can live with or without free oxygen. And in fact, many bacteria we find in a wastewater plant will actually fall into this group. So they will produce different things. And but again, if you want to optimize the treatment of wastewater, you're going to have more oxygen and bacteria will grow aerobically. We're going to go in now in a section of this presentation where we're going to do a little more math. Mentioned earlier on about food to microorganism ratio as a way of putting a number on our operation, and sludge age is another of those numbers that we have, and it is a measure of the length of time solids have been in the aeration basin or in the treatment plant. So we have this as days, and it is the pounds of MLSS in aeration basin. This is the solids. This is not just the bacteria that we talked about earlier as MLVSS. This is MLSS, and is the divided by the pounds of TSS coming in as influent daily. And one of the ways that we can think about sludge age, and it's not an exact equivalent, but it's similar, is we can say that sludge age is really the inverse of the food to microorganism ratio. Remember, food to microorganism ratio is the pounds of BOD in the influent divided by the pounds of MLVSS in the aeration basin. And here we have sludge age as pounds of MLS in the aeration basin divided by the pounds of TSS in the influent. So long as you can measure these two parameters, then you can determine sludge age. So the next slide is going through an example of how we would determine sludge age. So we have a 9.7 million gallon per day facility, and the influent flow into that is 8.3 million gallons per day. The TSS concentration is 174, and the MLS concentration is 4,744. So what is the sludge age of this facility in days? So here is our formula. We need to do 2 pounds formulas here, calculate pounds of MLSS and pounds of TSS. So the pounds of MLSS is 9.7, okay, times 8.34 times 4,744, which gives us 383,780 pounds MLSS. The pounds of TSS coming in is the flow, 8.3 times our 8.34 constant times 174 which is 12,044 pounds of TSS. And if we divide those two numbers one into the other, we should get 31.86 days. So again, sludge age does have units. It's always in days. Food to microorganism ratio is simply a ratio. So here is another math problem for you to try on your own. Again, the numbers here are very straightforward. There's no conversions to be done. It's just a matter of those two pounds formulas. Again, if you want to pause this recording until you've completed the calculations and then restart. In a couple of seconds, I will show the answer and then go to the next slide to show you how we calculated that answer. So the sludge age for this facility is 25.35 days. The next slide will show you how we work that out. Our pounds of MLSS in the basin is 7.5 times 8.34 times 33 and 75, which gives us the pounds of MLSS at just over 211,000 pounds of MLSS. Now, how much TSS came in? And again, here is our flow into the basin. Here's our TSS concentration and our constant 8.34, which gives us 8,300 and so pounds of TSS in the influent. And again, if we divide those two numbers together, this is how we get to 25.35 days. Now, one of the other questions we can ask ourselves, since we know that sludge age is a good indication of how well our plant might be operating, is that we want to change the sludge age. We've been going along and we calculated and it's not what we need it to be. For example, we calculated it as 22.5 days, but we really need to get it closer to 10.5 days. And the way we do that is to waste sludge, because here is the amount of MLS in our aeration basin. So in fact, what we want to do is to reduce this. But the question is, how much? So this is an example of a math question in both the manual and the study guide, and might be a type of question you might see on the test. So this is how we would calculate how to solve this problem. We can take this formula and we can rearrange it to calculate the pounds of MLS in the aeration basin equals the sludge age times the pounds of TSS in the influent. And what we do is we bring this to the other side of the equation, and instead of being a dividing number, it's actually a multiplication number. You can see that here. So what we do is we calculate the pounds of MLSS needed for the new sludge age and subtract it from the original MLSS to find out how much pounds we need to waste. So pounds of TSS in our influent, if you go back over those numbers, it's 1.2 million gallons per day times 121 times 8.34 gives us 1,210 or so pounds in the influent. If we look at pounds of MLS at 22.5 days, Here is our pounds of TSS in the influent times 22.5 days, and that gives us somewhere a little over 27,000 pounds of MLSS at this sludge age. But we want to make it 10.5, so the amount of MLSS at a sludge age of 10.5 is calculated by this formula, where we have the pounds of TSS coming in times our sludge age, and that gives us 12,715 pounds. So how much do we waste? Well, we take what we have minus what we calculated we need here, and if we subtract this number from this number, we need to waste about 14,500 pounds of MLSS from our aeration basin. So again, this is how we solve this problem of how much you need to waste. And again, if you need to go back over this, of course, you can rewind the recording a little bit and follow on this method. One other parameter that you might have come in contact with or might employ at your plant is something called the mean cell residence time, or MCRT. And MCRT really is a very sophisticated way of calculating sludge age. And as a definition, it is the amount of time in days that solids or bacteria are in the activated sludge process. Again, like sludge age, it is an operating parameter that can be key to make sure that you're running your plant as optimally as possible. So the daily wasting of activated sludge should equal their daily growth. If you waste too much, you're reducing the number of bacteria. If you waste too little, you're building up your solids. And so what is produced per day is really what you need to waste to make sure that everything is operating as optimally as possible. So some of what you produce is going to be lost in the effluent. And so we have this calculation to take into account when we're trying to calculate the sludge age, or MCRT. So MCRT depends on how much is wasted and how much is lost in the secondary effluent to put this calculation together. So let's look at how we would do this. So the MCRT is essentially 3 pounds formulas. I remember sludge age was 2 pounds formulas. MCRT is 3. Here we have the pounds of MLSS in the secondary system, and how much is wasted, plus how much is discharged in the effluent. Remember that sludge age was the amount coming in. MCRT, we use how much is leaving. So the MCRT calculation requires just the solving of 3 pounds formulas: the pounds of MLS in the system, the pounds of suspended solids that we waste, and the pounds of suspended solids that leave the plant in the effluent. So let's look at these calculations, and this is an example of a plant. We have a basin here. Its capacity is 0.75 million gallons per day, and we know the concentration of MLSS in this is about 2,500 milligrams per liter. We know the influent flow is 0.56, and anytime you see an influent flow, that is going to be the effluent flow. So just because we don't give you the influent flow, we've given you the influent and it's the same. We know that the suspended solids that are leaving the influent as the effluent is 14 milligrams per liter. And we know that we waste 11,000 gallons per day at a concentration of 1%. Now, there's lots of different numbers in here that you might not have seen before. So I'm going to go through this slow and steady. And again, if you need to go back over this, you can replay this. This is can be seen in the manual as well. So the question that we're going to pose here is, what is the MCRT for this extended aeration basin, 7.75 million gallons per day? The MLS concentration is 2,550 milligrams per liter. The influent flow is 0.56. The effluent TSS is 14 milligrams per liter, and the waste sludge flow is 11,000 gallons per day at a 1% concentration. Now, on your formula sheet, you should see a conversion for percent into milligrams per liter or parts per million. We'll go over this with slowly and steady in the next few slides. So remember that I said that the MCRT calculation is really just 3 pounds formulas. So the first pounds formula you are going to calculate is the number of pounds of mixed liquor suspended solids, MLSS, in the aeration basin. And here we have our numbers, 0.75, 2550, here's our conversion factor. And if we plug all those numbers in our calculator, we should end up with something a little shy of 16,000 pounds of MLSS in this aeration basin. What's the second math formula, second pounds formula we need to calculate? And this is the amount of sludge wasted. So on your formula sheet, you should see that a 1% solution is actually 10,000 parts per million or milligrams per liter. And we're going to have to convert gallons into million gallons per day. So 11,000 gallons is 0.011 million gallons per day. And if we put those three numbers in, concentration, million gallons per day, and here's our 8.34 pounds per gallon, we are going to waste something like 917 pounds of TSS per day. Now for the last and the third formula, pounds formula, we need to calculate the number of pounds of TSS that are discharged in the effluent. As I said earlier, the effluent flow has got to equal the influent flow. Either that, if it doesn't, then you're emptying all your wastewater treatment facility, or it's overflowing into the street. So always make the assumption that the two flows leaving are going to be the same as the flow coming in. So here's our TSS of 14 milligrams per liter. And again, here is our numbers. Here is our flow, 8.34 times 14. And we're actually discharging just a little more than 65 pounds of TSS. So we have our three numbers. We've calculated our 3 pounds formulas, and we really just need to put them together. So what we have got so far is 15,950 pounds of MLSS in the aeration basin. We've wasted 917.4 pounds of TSS, and we have discharged 65.39 pounds of TSS into the receiving waters of the Commonwealth. So we just put these three numbers in our MCRT. You can see it here. It's on your formula sheet also. And if we put those numbers in, our 982 is the sum of these two numbers. We have an MCRT of 16.25 days. Now notice that we've given you two math formulas for a sludge age and MCRT. They are not going to be the same. So whatever MCRT you get and you know that your plant is working well, this is what you need to aim for, which is why, like sludge age, it's the amount of TSS that you're wasting is going to influence the number of days of MCRT. You don't want to put too much in the effluent because that's going to get you in trouble with the division of water. And again, the amount of MLS in your basin you want to optimize also. So here is a question for you to solve. And I will tell you that this we have this in the manual and in the math study guide, and it may be the way that this information is given to you on a test. We may have it in a word problem if we have something like this, but I will tell you that there is certain information in here that you do not need. I'm not going to tell you what it is. You can try and figure that out. We will come back to this. I will give you whatever time you need to solve this math problem. So pause the recording, and then when you're ready, you can restart it, and you will see the answer being shown up, and then we'll go over how we solve this. So I'm going to wait a couple more seconds before I do the animation that will show you the answer, and then I will go to the next slide to see how we calculated MCRT. So MCRT in this math problem is 10.87 days. So the next slide will show you how we solve this problem. Okay. There are information in here, and I hope on your monitor that you can see that I have highlighted numbers in orange, in light blue, and these are in a purple color. What I didn't highlight was MLVSS, return sludge, and influent BOD. Now, some of these would be very important in calculating food to microorganism ratios or other parameters, but they are not necessary for MCRT. So let's look at how we use this information to get our answer. So our pounds of MLSS in our oxidation ditch. Here we have, and this is highlighted in orange, this is the volume of the ditch by the concentration of MLSS. Here's our 8.34 conversion constant, and that gives us a little over 105,000 8,000 pounds. Now we want to know how much is wasted. No, actually, we're going to talk about how much is in the effluent first. And here is the numbers in light blue. So our flow, our influent flow is the same as our effluent flow at 2.8 million gallons per day. Here's our effluent concentration, again, our constant, and we have wasted a little over 1,260 pounds of TSS. So finally is how much we have wasted. And again, these are the numbers that we have pulled that here are in purple. So our concentration, we've given you this in parts per million, and we could have given you this in percent, but we didn't want to make it too difficult, too many conversions. And here is your flowing gallons per day, which we have to convert into million gallons per day. And again, the amount we waste is 8,406, so pounds. So here are 3 pounds formulas, and this is, we just now will plug and chug these into the MCRT formula. This is what we have. This is our MCRT formula, our pounds in the secondary system, divided by the amount we waste, plus the amount in the effluent. And we put those numbers in. We have 105,000 pounds divided by 9,667 pounds. And that gives us our MCRT of 10.87 days. So if you ever have an MCRT question on a test, just break it down into 3 pounds formulas, take your time. We do many pounds formulas. They should be very familiar with them. Just know what's on your formula sheet, know how to calculate them, and you should be okay. We're going to go back now. We had talked earlier about oxygen. We're now going to look at the effects of some other parameters on how well the activated sludge process goes. And this is concerning the effect of pH. pH is important because the enzymes that do the work of breaking things down in the extracellular matrix or slime are pH dependent, in that if the pH is not optimal, they don't work very well. This is why we should keep the pH between 6.8 and 7.2, because most enzymes will operate well within that range of pH, and therefore the organisms will grow well and treat the wastewater in the most optimal way that we can. We've already talked about food to microorganisms ratio, and we'll come back to it again because it is a parameter that you can calculate and keep close to that ratio to make sure that there's enough food and there's enough bacteria in the right ratio to do the most optimal treatment of the waste. So we can control this F to M ratio by wasting sludge. And then if we need to increase that F to M ratio, we increase the sludge wasting because sludge is predominantly bacteria, about 95%. So by lowering the number of bacteria, by wasting them, you're going to increase the F to M ratio. And the same, if you want to decrease it, then you decrease the wasting of sludge. Why would we waste sludge? It's really because we can't change the food. What's going to come in is what's going to come in. And the one aspect of this that you can control is the wasting of sludge. And just as an idea of how much sludge you would make, the idea is that for every pound of BOD that you're going to take out of the wastewater system as it comes in, half of that is converted to solids, to cell material. So the other half of that is really used for energy. So again, controlling the F to M ratio, very similar to altering the sludge age or the MCRT, is some of the best ways of optimizing how well your plant is working. And of course, you do this by wasting of sludge. So what you need to know in order to control this well is how much food is coming in, the amount of flow that's coming in, and of course this will tell you the effluent flow rate also. You're going to have some return activated sludge, and in order to optimize this process, you're going to need to know the amount of solids in that activated sludge and its flow rate. So wasting sludge and returning sludge is allowing you to control the amount of solids in the plant, and that will help you optimize the treatment of the wastewater. We talked earlier about oxygen, and then we've discussed pH, and now the role of temperature. All biochemical reactions are temperature dependent. Lower temperatures cause things to grow slower. Higher temperatures make them go a little faster up to a point. Since you can't change the temperature of your wastewater treatment plant, it's very much dependent on the season. So in the winter, because things are slower, you're going to need more bugs than you would do in the summer. Interestingly enough, that colder water holds more oxygen, but biochemical reactions are slower. There's less oxygen in the summer, which is why we often will make sure we have aeration in a plant to make sure that we are having our 2 milligrams per liter of DO. So earlier on, I'd mentioned there are different ways of classifying bacteria, putting them into groups. We talked earlier about oxygen levels, and here we're going to talk about the ranges of temperature in which bacteria do well. There are a group of bacteria, they're called psychrophilic, and they will grow at really low temperatures. These are the ones that you find in your fridge that make things go bad. Most bacteria we call mesophilic. They grow at room temperature, 68 degrees to 113. I know 113 is a little high for room temperature, but this is what you're going to see mostly in nature. And the final group are things that are called thermophilic, and these grow at really high temperatures. You find these in hot springs, at the bottom of the sea, in volcanic vents, and biotechnology and the medical field has found these types of organisms very, very useful because we didn't think that they could exist at temperatures that they do this high. One of the things is you can destroy bacteria by heating them, but don't rely on cold temperatures to kill bacteria. That's a FYI comment for most people. One of the other things that we'll find in wastewater, especially if you're pulling in from industrial sources, are things that can cause problems. We can call these toxic materials or priority pollutants. And there are on the EPA list about 126 of these. They include metals. I've showed you the metals here. I'll go over these again. But herbicides, pesticides, products of combustion, volatile organic materials, and synthetic materials. If you want to look at this list, this is the website to go to, or you can just type in and search for priority pollutants. So if you think about these metals, if you know that your sources might include industrial processes, these are the metals you are going to test for on a regular basis. We call these the priority pollutants, and they're really considered quite toxic. However, there are others, arsenic, cyanide, silver, and mercury, that if you can show that you never see these, we're not going to discuss them anymore, but initially in your plant you will test for these. And we'll talk about these metals later on when we talk about certain industrial processes. So priority pollutants are going to need a pre-treatment before they can be treated in the wastewater plant because of their toxicity, and because most of them are metals, they can be treated by coagulating them, and therefore they will come out of solution. They can be precipitated. The solubility, the amount that they come out as a precipitate, is dependent on their pH. So pre-treatment is just adjusting the pH so that the metals come out of solution, can be precipitated out. Of course, then you've got to adjust the pH back before it gets into the wastewater plant, due to the narrow range that the bacteria can tolerate. A couple of other things to consider during wastewater treatment is you have to mix things in order to bring the bacteria, the nutrients, and dissolved oxygen together. You can imagine that if you didn't mix, things would settle out and there wouldn't be much oxygen on the bottom of your treatment system. If you don't mix enough, of course, things aren't optimal, but if you mix too much, certainly in the early part of the process, you can break up those small clumps of bacteria and extracellular matrix we call floc, and then it doesn't settle. Also, if you have a system, circular basins are more prone to this than rectangular ones. There's a process of short-circuiting, and short-circuiting is simply the matter that material flows through certain parts of the basin, not all the way through the basin. And depending on the design of your plant, and if you see short-circuiting, this needs to be dealt with and avoided at all costs. Another parameter that you are going to probably deal with at some point in the wastewater system is inflow and infiltration. This is due to rain events that can either flow in very quickly, inflow, or more slowly, infiltration. And this is because our sewerage system isn't perfect. There are leaky pipes, there are broken pipes. Rain events can be very sporadic. So if this is an issue for you, then the way that you can lower the potential impact of I&I is to, before flow gets into your plant, you can set up equalization basins so that the water flows into these basins first and you draw off what you need. You can have collection detention basins, or probably the most expensive is to repair the whole sewer system and rehabilitate it, repair it, or replace it. A couple of other things that can happen to your wastewater plant that you don't necessarily design for or plan for are what we call shock loads. These are increases in the organic loading to the system. Organic material meaning food. And we know that the food to microorganism ratio gives us a ratio that is optimal for the plant, but you get too much food coming in, and nutrient loads, you might not be dealing with this very well. So for example, if all of a sudden you get a whole bunch of septic tank unloadings, whereas our normal range of BOD might be 160 to 280 milligrams per liter, this is in the thousands. This might be disruptive to your system. So the shock loads are increases in organic loading to the system. The other type of insult to the system might be something that we call slug loads. These are spills of unknown origin. You see that I've highlighted this in orange because you don't know what they are. They could contain toxic materials. They could be harmful to the plant operation or even to the operator themselves if you don't know what has come in. If this happens to you, it is important that you determine as quickly as possible what has come into the system, where it came from, and how much of it that you may have to find another way to deal with. So the next set of slides deals with specific industrial systems that you might have coming into your wastewater plant. Industrial wastewater, because of the processes involved, probably have loadings far in excess of what you would see in domestic wastewater. Remember those population equivalents of 100 gallons per person per day, 0.2 pounds of TSS. And so industrial wastewaters, if they're not pre-treated, they can have a huge impact on the effective operation of your plant. And of course, these can be shock loads, organic material, or slug loads, known material that you have to deal with. So this next set of slides just indicates the sorts of issues that you might have to deal with if you know the specific types of industrial wastes that may come in your plant. So tannery waste, these are the treatment of hides, leatherworking, salts, a lot of salts, different types of salts are used in the treatment of leather. We can have high BOD, we can have high TSS, And again, pretreatment is probably necessary before the water enters your plant, which is a biological process. Dairy wastes, again, the BODs can be very, very high. And if this is happening to you, then flow equalization and maybe some chemical precipitation is required. You might have to add more nitrogen phosphorus because of these high ranges of BOD. Pulp and paper wastes, again, high levels of BOD, and again, hopefully pretreatment has taken a lot of these materials out. And again, you might need to add nitrogen and phosphorus to balance those C and P ratios. Meat processing wastes, again, very high levels of BOD. Remember, you're dealing with meat, as that's organic material. Again, a lot of water is used during the process of meat treatment. Because it's meat, grease is an issue. And so a way of treating this might be dissolved air flotation, since this is grease floats to the top. Anaerobic and aerobic digestion might be good ways of also doing a tertiary treatment of these wastes. And like every other industry we've talked about, pre-treatment is probably essential at the plant. Fermentation wastes, again, higher levels of BOD, high levels of water is used in the brewing of beer. It's interesting to make note of the fact that antibiotic production is a fermentation waste. And so a lot of our companies that make antibiotics are also going to contribute to having to have some pre-treatment before it gets into the wastewater process. So again, high levels of BOD with antibiotic treatments, biological trickling filters and anaerobic digesters might be more optimal methods to use than aeration basins. And again, because of the high levels of BOD, you might need to supplement levels of nitrogen and phosphorus to get those correct C and P ratios. Fruits and vegetable waste, if you've got facilities that process fruits and vegetables, BOD can vary depending on the type of processing you're going to do. But because you dig things out of soil, make sure you have either in the pre-treatment or in your plant good grit removal if a lot of root crops are used. Again, nutrient deficiencies, and depending on the types of plants and the season, you can treat them well as long as you are aware of what's coming in and they're not too much of a shock or a slug load that overwhelms the system. Textile wastes, if you are dealing with natural fibers such as wool or cotton, and then you've got issues of dirt, grease certainly in wool. These have to be taken care of. If you're doing synthetic materials, then the processes of making these and dyeing them also will add a lot of metals to the waste, which have to be dealt with pre-treatment. And again, the ways pH adjustments, flow equalization, treatment of metals, and of course, ways of getting rid of detergents, because you need to wash the textiles before they go to the next part of the process, are all issues that you will have to deal with if textile wastes are a significant part of your influent. Oil and petroleum wastes, especially if we're looking at fracking, brine is the main waste that will be produced. Hopefully this will be treated before it gets into your plant. Solar evaporation can do a good job of removing the brine. And again, pre-treatments, separating what oil is in the water, chemical coagulation of metals, and then precipitation and sedimentation are very useful pre-treatment processes. Metal finishing wastes, if you remember when I showed the slides of the priority pollutants, these were the list: copper, cadmium, nickel, zinc, and chromium. These are all metals that are used in plating, and we might have low pHs, tin, and cyanides that will be produced during the plating methods. So again, if you're an industry, you should be removing these in the pre-treatment before it gets to the water treatment plant. Something very important to understand, that if you have cyanide waste that you have to treat, then the most optimal way of doing this is by a process called alkaline chlorination. That is chlorinating at high pH. Chlorine is a very good oxidizing agent. And the reason we do it at high pH is that if we were to do it in acid conditions, reaction of acid and cyanide produces hydrogen cyanide gas, which is extremely toxic. So cyanide wastes, treat by alkaline chlorination. Activated carbon can be a very effective tool in emergency treatments of water systems. And in fact, it's always good to have some on hand for that very reason, because carbon will basically mop up a lot of things, a lot of organic material, such as PCBs, phenol and phenol-like compounds, and other solvents, reduces color, taste and odor issues that might be still present in the water, even though you've treated it as optimally as you can. So we produce activated carbon from a lot of sources, of course, wood, coal, nutshells, bone. Sawdust comes from wood. And basically, you dry the raw material and heat it in the absence of air. So all the volatile materials come off, but you don't burn because you don't have the oxygen. If you're going to use activated carbon, the activated carbon needs to be in contact with the water for a sufficient time to completely absorb things. We look at this as a detention time of up to 30 minutes. Don't think that a minute contact time is going to do this removal by activated carbon. So we can look at those efficiencies by measuring COD or turbidity, These are very quick results, methods that give very quick results. And if we are thinking of using activated carbon, then a hydraulic loading rate of 2 to 10 gallons per minute per square foot of carbon is optimal, and our organic loading of 0.5 pounds per day per pound of carbon. Anything excess of that, the carbon won't absorb it. One of the interesting things to remember is that high TSS concentrations over 20 milligrams per liter will what we call blind the carbon, i.e. bind to the carbon and block the absorption of other things that are in solution. If it does so, the flow is going to be reduced and you're going to lose pressure. So I think this may be the final slide before the end of this. And this is a reminder to be able to distinguish between absorption and adsorption. Absorption is taking in or soaking up into the body of an organism through the cell wall, cell membrane. So this is absorption, is going into the body, the way that tree roots absorb nutrients in the soil. Adsorption, on the other hand, is just the sticking of substances to the surface of the material that is going to adsorb it. So in the case of carbon, carbon adsorbs materials onto its surface. It doesn't actually enter into the carbon at all. So finally, activated carbon adsorbs. This is the end of chapter 3, biology. And as always, we give you 2 ways to contact us. If you have questions or comments, we can be contacted by email at envhelp@ky.gov or by phone at 502-782-6189. This concludes chapter 3. Thank you very much.